Hey, Algebra 2, it's Mrs. Mack. Hope you're doing well. Here is our first go at our lesson. We're going to be looking at right triangles this week. And this week really is a review of everything from geometry about right triangles. So this should look familiar to you. But if you got a chance to print off the right triangle summary sheet, this will be a nice set of notes for you to refer to as you do the problems this week. If you didn't get a chance, you can pause and do that right now, or just grab a notebook and you can write some things down. So there are really three things that we're going to be looking at today as review. The first is review like way back to 7th, 6th, 7th grade, something like that. It is the Pythagorean theorem. Remember what that says? That says if you've got a right triangle, these only work within right triangles. So that little square right there means that if you take a squared plus b squared, that will equal c squared. That is our Pythagorean theorem. And some things to remember about that formula, a and b, those are the two legs that come together to form that right angle. Those are called legs. And C is that longest side directly across from the right angle. That is the hypotenuse. So in all our problems, I'm going to assume that you are familiar and can use that Pythagorean theorem to find a missing side of a right triangle. Then, if you recall, we have some trig ratios. When you begin to make a ratio, a fraction of two of the sides of any right triangle, they will have the same ratio if the angles of the triangle are the same, so in similar triangles. So you remember that there is a ratio for the sine. The sine of an angle is taking the opposite side and putting it over the hypotenuse. So if we look at the sine of A, that means to sort of sit in angle A, this capital A here, and the sine of angle A would be taking the side opposite angle A. So you walk out side A, and the side that you would hit would be little a. The opposite would be little a. And then what's the hypotenuse of that triangle? That's always across from the right angle. That is C. So the sine of angle A is A over C. I'm using that line as a fraction bar right there, the opposite over the hypotenuse. And you can be in the other angle as well, angle B, and this changes your perspective. So the opposite is a different side. The opposite of angle B here is little b, and the hypotenuse stays the same. In a right triangle, you always just have one hypotenuse. So that's the sine function, opposite over hypotenuse. And we begin to write this acronym. Sine is opposite over hypotenuse. And some of you are going, oh, I remember that. That's so. And then the second part is CAH, which leads us to our next trig ratio, the cosine. The cosine is the adjacent over the hypotenuse. And remember, adjacent means next to. So if we look for the cosine of angle A, from angle A in here, there are really two sides that are adjacent to angle A. It's the two pieces that make up that angle. It's either side B or side C, but C already has a role. It's the hypotenuse. So angle B is the adjacent. It's the side next to angle A that's not the hypotenuse. So this would be adjacent over the hypotenuse of C. And then if we change perspective and look from angle B, the adjacent side there is side A, because A and C are both adjacent, but C is already the hypotenuse. So this will be A over C. That's that CAH. Cosine is adjacent over hypotenuse. And then we finish it off to get SOHCAHTOA. That's how we remember these trig ratios, and that is the tangent, and the tangent is O, the opposite, over A, the adjacent. So tangent, I think I spelled that wrong, adjacent. There we go. Tangent is opposite over adjacent. So looking from the perspective of angle A, the opposite is little a. The adjacent, the side next to it that's not the hypotenuse, is B. So the hypotenuse isn't involved in the tangent at all. From angle B, the adjacent would be side, the opposite would be side B over the adjacent of side A. And those are our three trig functions. Hopefully that feels familiar to you. Then the last piece of review here is looking at some special right triangles. The Pythagorean theorem works for these triangles. Trigonometry ratios of SOHCAHTOA, sine, cosine, tangent, also work for these, but there are some very special things that occur if you have a 45-45-90 triangle. This would be an isosceles right triangle. In any isosceles triangle, we know that the sides opposite same angles are also the same. So if this side is length x, this one is also length x because their opposite angles are congruent. And then that hypotenuse, you could go ahead and do the Pythagorean theorem. That's actually how this special right triangle is derived. If you have x, this becomes x times the square root of 2. What's nice is if I remember this special right triangle, I don't have to do any calculations. I don't have to grab my calculator. I don't have to remember the Pythagorean theorem. I just remember that it's the side length times root 2. Now, in a 30-60-90 triangle, now this obviously is not drawn to scale, but if this angle is 30 degrees and this angle is 60 degrees, the side opposite the 30 degrees, that is really the base of this 30-60-90 triangle. So it is one of the legs. The smaller leg would be across from the 30-degree angles, and if that is any value x, this hypotenuse is twice that length. It's going to be twice as much as that smallest leg. And then the leg across from the 60-degree angle is going to be the smaller leg times the square root of 3. That should look somewhat familiar from geometry. How do you remember that? Well, I look at the 45-45-90. Two of these sides are the same, so there must be a root 2 involved. I look at a 30-60-90 triangle. These are all multiples of 3, and so there must be a root 3 involved. That's how I remember it. You can figure out your own little gimmick to remember that piece. Now, let's look at a couple examples so you can do the homework. We're going to put these pieces to work. You can go ahead and flip that page over or move on in your notebook. I'm going to look at this example right here. All right, so I'll give you a second. You can draw yourself a right triangle, and some of you might be looking at that picture going, what in the world are those things in the angles? These are Greek letters. I want you to get used to these because as you go on in mathematics, we tend to represent angles with Greek letters. This is a theta, T-H-E-T-A, theta. It's like a 0 with a line through it. This over here, it's the little side squiggly fish-looking thing. That is an alpha. So those are two Greek letters that we often use to represent angles. So what I want us to do is I want us to figure out what is the sine of theta, the cosine of theta, and the tangent of theta. In order to do that, I really do need all three sides of my triangle, and one of them's missing. So hopefully you think, oh, I need to use the Pythagorean theorem. Remember, legs squared plus legs squared equals hypotenuse squared. That is that c squared. And some of you might recognize this as a Pythagorean triple, but if you don't, that's okay. This is 225. And that becomes 289 when you add them. You can take the square root, and c is equal. When you take the square root, you do need to take plus or minus. 289 is a perfect square. It is plus or minus 17. But of course, when we're dealing with triangles, we do not have negative side lengths, so we are just going to use the positive 17. So in some of the examples in the homework, you'll have to just find that missing side so that you can do the trig ratios. Now I'm going to live in the land of theta. Sine is opposite over hypotenuse. So the opposite, I just walk out of that angle, and the opposite side is 15 over the hypotenuse is 17. There's the sine of theta. The cosine of theta, so ca is CAH, adjacent over hypotenuse. So the adjacent side is 8 over the hypotenuse of 17. And tangent TOA, the opposite over adjacent, opposite is 15 over the adjacent, which is 8. Now let's just change perspective. Can you do the sine of alpha, the cosine of alpha, and the tangent of alpha? It's just fun to draw those Greek letters. All right, sine is opposite. Opposite would be 8 over hypotenuse of 17. Now that's a familiar fraction. Look at that. The sine of alpha is actually the same as the cosine of theta. If we were in class, we would explore that a little bit more, but you might want to ask yourself, why are those two the same? And see if you can convince yourself. Cosine of alpha, adjacent, which is 15 over 17. Notice again this connection right there. The sine of theta was equal to the cosine of alpha. Why is that true? Think about those sides, those opposites and adjacents, and that perspective. Tangent of alpha, opposite over adjacent. Again, look at that. The tangents are reciprocals. When you change where your perspective in the triangle is, it changes what is the opposite and adjacent, but it doesn't change the hypotenuse. So there are our 3 trig ratios for those angles. All right. I just have a couple more examples for you with some special right triangles. Look here, I have a right triangle. I need to make sure it's a right triangle. It is 45 degrees, so that automatically means that this is 45 degrees. So 45, 45, 90 triangle. Here, this leg is 12, so the other leg happens to be 12. And then remember, I can find that hypotenuse. I don't have to use the Pythagorean theorem. In fact, I don't want to. I want an exact answer. I take that side length of 12, and since it's a 45, 45, 90, I'm going to multiply it by root 2. Now, take a look at this example. This almost looks the same. It is also a 45, 45, 90 triangle, except the hypotenuse is 12. So how do you go from knowing the hypotenuse to gain the leg? Up here, we knew the leg and we multiplied it by root 2 to get the hypotenuse. So we're going to undo that, use that inverse function. Instead of multiplying by root 2, I'm going to divide by root 2. And so that side would be 12 divided by root 2. And this would also be 12 divided by root 2. Now you can leave it like that. I'm fine with that. There are lots of math teachers out there who like you to not have a radical in the denominator, so they would say rationalize that denominator by whatever the radical is, multiply top and bottom. That's a form of 1. And so then this would be 12 root 2 over, let's see, root 2 times root 2 is 2. And then you could divide 12 by 2 and get 6 root 2. That's a little bit nicer form. Sometimes it is, sometimes it's not. And so it doesn't matter to me at this point which you do. All right, last two. This is a 30-degree angle. This is a 90-degree angle. That must make this a 60-degree angle. Well, a 30, 60, 90 triangle. The base, the anchor leg, is going to be the piece across from the 30-degree angle, that smallest leg. This is always half of the hypotenuse, or the hypotenuse is always twice the smallest leg. So this must be 25. Then to find that longer leg, just take the small leg and multiply by root 3. So I always try to look for this one down here, that anchor, see if I can find that first, if I don't already have it. Now if we just move things around just a little bit, notice I still have a 30, 60, 90 triangle, but now I know that longer leg. That was the one that was the smaller leg multiplied by root 3. So to get back to that anchor leg, I'm going to take that bigger leg and divide by root 3. Again, you can leave it just like that. I kind of like it. And now to go from the smallest leg to the hypotenuse, you have to double it. So this was 100 divided by, 50 divided by root 3. So doubling, I got ahead of myself there. It would be 100 divided by root 3. So that gives you a brief little summary of right triangle trig that you did in geometry. And so now you should be equipped to finish the homework. All right, see you next time.